Hello everyone, welcome to 𝐿ustraca. In this lecture, we are going to see the crack width analysis of RCC section as per IS 456-2000. There are different, various gaps in the explanatory, or you can say in the clauses given in IS 456-2000 for crack width analysis. So we'll try to fill those gaps through this session while calculating the crack width in a RCC section. So let us jump into the code first to see what code is given. So here you can see the annexure F, clause 35.3.2 and 41.3 IS 456-2000. They have given the design surface crack width. So this crack we are going to calculate at the surface of the section. Okay, and this crack is basically due to the bending, the tension due to the bending. Okay, so you all know that when we will be getting the cracks when the concrete is under tension. Okay, so in this condition, suppose this is my beam. Okay, so these cracks will, the crack width calculation or crack width formula that is given in IS 456, it is for the cracks which are coming in a section, or you can say in a member, due to the tension which is generated by the bending of the member. Okay, so suppose we have this, the section is subjected to bending, and then we can see the cracks here, right? Why these cracks are coming? Because this particular in this particular portion the fibers are subjected to tension, right? And due to this tension, these cracks are being appeared in the section, right, or in the member. So now calculation of crack width of this condition is given in IS 456-2000. Okay, so if you have any condition where the members are subjected to here I can write here tension due to bending. Okay, it is tension due to bending, and the crack is also due to this condition. But when the member is subjected to, the concrete member is subjected to direct tension. Okay, so the direct forces, suppose this is my member, and suppose I have this direct tension force like this, kind of like this, just for example. So in this case also, as the concrete is not capable of not capable of taking tension, so in this case cracks will generate, right? So cracks due to the direct tension, and the crack width, which is how you can calculate the crack width for those cracks which is coming due to the direct tension, is not given in the IS 456-2000 code, right? So we will just for your clarification, so that if you get any condition where you are getting direct tension, you should not calculate the crack width using this particular methodology. Okay, so now first of all we will see what is the crack width formula that is being given in IS 456 annexure F. So if you see the annexure F as said that design surface crack width WCR is equal to 3 ACR, this is epsilon m 1 plus 2 into ACR minus C minimum by H minus X. So these things we will be first writing here, and we will try to understand one by one all these terms. Okay, so first of all let us write the formula. It is WCR, let me change the color, it is design crack width. Okay, so WCR equal to 3 ACR, okay, multiplied by epsilon m 1 plus 2 into ACR minus C minimum divided by H minus X. This is what code is given. Okay, this is what code is given, correct? Now what is this what is this, what are these terms that we need to understand first, right? So first of all, what we need to understand, suppose let us take one section. Let me just draw a section here. Okay, suppose this is my section. Fine. So I am providing some reinforcement here, and this is subjected to tension due to the bending. Correct. So this reinforcements will be taking the tension because we assume that the concrete will not take any tension. Correct. Okay. So what we are saying that now let us just write the dimensions. Suppose this is my B and this is my D. Okay, this is my B and the vertical one, I mean the vertical dimension is my B, and we are going to calculate the crack width at this surface, because this face is subjected to tension. Correct. So here we are going to calculate the you can say let us write point of interest for calculation of crack width. Correct. So at this particular surface we are going to calculate the crack width. Okay, so if we just denote that the distance from the top compression phase, this is my compression phase, right? The distance, why I'm writing this you will understand in a while. So compression phase, so the distance from the top compression fiber or top compression phase of the phase where we are going to calculate the crack width is, suppose this is suppose A. Now see, you can calculate crack width anywhere at any phase, right? Any section, but our point of interest is this because it is surface crack width, right? Already mentioned in the code. So that's why we are going to calculate at this particular surface, which is subjected to the maximum tension, you can say, and this is the distance from the compression phase of the member, right? So what we can write here, from here, this we can write that A equal to D. Correct. A equal to D. Now here this H which is mentioned in our code, this H is nothing but the depth of the section. Okay, this H is nothing but my depth of section. So what we can do, we can change this, I mean we can change this you can say nomenclature from H to D for our better understanding, right? So let us start from here. So WCR equal to 3 ACR, one by one we will understand. Okay, epsilon m 1 plus 2 ACR minus C minimum, okay, divided by D minus X. Correct. D minus X. So D we understood, it is the depth of the section, which is equal to D, actually H equal to D. So that's why we have replaced this H by D for our better understanding, right? Now let us draw the section again here for some more explanation. This is my section, okay, subjected to bending. This is my reinforcement. Okay, this is my reinforcement. Okay, so now if I just take any of the color, change it to suppose blue. Okay, so this is my centroidal axis for the group of, I mean for the bars that we have provided. Correct. Okay, so this depth is nothing but my effective depth D. Okay, now if you draw the neutral axis here, suppose this is my neutral axis. Okay, suppose N is my neutral axis, correct? So what is the depth of neutral axis? So from the compression phase, top compression phase, this is my depth of neutral axis. Now see, it can be at the top also, because suppose you have hogging, so it will be just opposite case, correct? But for now we are considering that bending at the bottom. You can do the same for the other case also. So this is my neutral axis, x equal to my neutral axis depth, or depth of neutral axis. So this is what x is actually. This is what x is. It is my depth of neutral axis. Okay, it is my depth of neutral axis. So what is this dimension then? What is this dimension? So obviously it is my d minus x, correct or not? This is d minus x. Fine. So one more dimension, if you see, we have defined that we will be taking from the phase of the compression, from the compression phase, the point of interest for calculation of crack width is a, correct? So we can say that this distance, if we just extend this line, okay, so this distance, sorry, not this, from this face, this distance is nothing but my a minus x, because we are going to calculate the at this particular phase, we are going to calculate the crack width. So this is my a minus x, right? It is a minus x. Now we know a equal to d, so we can replace this a with d, so it will be d minus x, correct? Right? So we will do that. First of all, what we are going to do here, we need to understand one thing, that if you just open the code, you will see that the code has given that this epsilon m is nothing but the tensile stress, you can say, for a rectangular tension zone. This gives epsilon m. So it is nothing but the I would say, what should I write it here? Let me just see what should I write it here or not. One more thing. Okay, let me just keep it here. We will write it later. So now you understand one thing. If I just draw the stress strain diagram, I will come to this part later. Let us draw the stress strain diagram from here. Okay, I think this line is, I have to draw it straight. Okay, fine. So I'm drawing the strain diagram here. So the bars here are subjected to some strain, right? What will be the strain here? It will be FST by ES, correct? Stress in the bar divided by the Young's modulus of in steel, correct or not? Because what we know, stress by strain is equal to, so we know stress by strain equal to Young's modulus E, correct? Now if I want to find out the strain equal to obviously stress by Young's modulus. So this is what we have done, stress in the tension steel divided by the Young's modulus of the steel, right? ES, correct? So this is FST by ES. If we want to find the strain at this particular phase where we are going to find out the crack or crack width, so the strain in the concrete phase where we are going to find out the crack width, this if we define in terms of sigma epsilon 1, okay, this if we define in terms of epsilon 1, then now it is our job to find out the epsilon 1, because this particular thing we need to find out. Okay, why this particular thing we need to find out? Because now I will jump into the code. If you see here, the code says that this epsilon m. What is this epsilon m? That I will explain in a while, but let us just write it here. This epsilon m equal to epsilon 1 minus some thing which is b minus h minus x. I will just write it here as per code, b into h minus x into a minus x. These terms already you know. 3 into Young's modulus of steel into AS means area of steel. I will write it as AST divided by d minus x, small d minus x. That means effective depth minus x. Now this formula it is given in code, right? How this formula is coming, that I will explain in a while. Okay. So see why I am finding out this epsilon 1, because I need this epsilon 1 to calculate the epsilon m. Okay, to calculate the epsilon m I need this epsilon 1. That's why I am finding out this epsilon 1, which is nothing but the strain, okay, the tensile strain in this concrete surface where we are going to find out the crack width. Okay, so how to find out this epsilon m? How to find out this epsilon m? If you use the similar triangle formula. Okay, so what we can write in this from the similar triangle formula? So if you take this as one triangle, okay, and the bigger one, suppose I will just name it, suppose A B C and A D E. Okay, so from triangle A B C and triangle what should I write? It should be like this. Sorry, I will compare which values, these values AC and BC we will be comparing. So we will say from triangle BAC, right, or CBA, something like that, BCA. This also you can write. So just for understand that, let's not all confuse all these things. Just two these triangles we have, okay, ABC and ADE. So from this triangle what we can understand, so if we consider this as a, I can say, right angle triangle, suppose, okay, right? So in this case this is my perpendicular, this is my base, okay, BC is my perpendicular, AC is my base. So we can write BC by AC, correct, equal to BC by AC equal to how much? DE, okay, DE by AE, correct? From these two we can write. So what are the values of this? If you just write it here, BC is nothing but by FST by ES. I'll just write it here. Sorry, FST by ES multiplied by C divided by AC. So 1 by, what is this AC? AC we know it is D minus X. It is D minus X. Let me just draw this also. Okay. So AC is nothing but D minus X. So I'll just write divided by 1 by D minus X equal to then DE. What is DE? DE, if you see, it is epsilon 1, right? So epsilon 1 divided by AE. It is nothing but A minus X. A minus X, correct? So if I just write that, what is the value of epsilon 1 then? Then epsilon 1 equal to FST multiplied by A minus X divided by ES into D minus X. This is what we are going to get, right? This is what we are going to get, correct or not? Okay, so this epsilon 1, what is this? This epsilon 1, what is said? It is the tensile strain at the desired face of concrete, right? Desired face of concrete. Now we are calculating the you can say we are calculating the crack width at a distance a from the compression phase, correct? So that's why we got this a minus x. Now as we are finding at this particular phase, here we know a equal to d. So as a equal to d, because we are finding out at this particular phase, correct? So it is obvious, it is very obvious that a equal to this total depth of the member, which is the d. So as a equal to d, so we can rewrite the formula in this way, that epsilon1 equal to fst by es multiplied by d minus x. We are replacing a with d multiplied by small d minus x, correct? Okay, so we got this fst by es d minus x by small d minus x. So we got this epsilon1, okay, which is required to find out this em, epsilon m. And epsilon1 also we got what it is the tensile strain at the desired face of concrete. That means wherever you want, suppose this particular face of the concrete, so we know what is the depth from the compression phase and we use that here, correct? Okay, so epsilon1 is clear. Now you need to understand one more thing. What is this? What is this? So let me just write it here. Let me just open the code just to see what it is. They can strain at level considered calculated ignoring the stiffness of concrete and tension zone. Okay, fine. Okay, fine. So now there is one phenomena called tension stiffening. Okay, there is one phenomena called tension stiffening. Now why I am talking about this tension stiffening? So first of all, let us understand what is tension stiffening. Suppose we have a concrete section like this, okay, concrete section like this. We have provided some reinforcement, okay, at some distance, okay, fine. So what we assume, that the cracks are being generated, or cracks are being introduced, or it is coming at these locations between the reinforcement bars. The cracks are coming, correct? So the reinforcement between two, or you can say the area between two cracks, okay, so the stress in this particular reinforcement, suppose we have a reinforcement in this cracked area, so the reinforcement which is in the cracked area and the reinforcement between the cracked area, there is a difference in strain or difference in stress, because at the reinforcement which is in between two cracks, okay, so suppose this is crack CR1, this is crack CR2, so this reinforcement between these two cracks transfer, or you can say transmit, some stress in its boundary concrete, okay, transfer some stress in its boundary concrete, okay. So what happens, due to the transfer of stress from the reinforcement to its boundary concrete, the stiffness of this concrete in this between two cracks, okay, between two cracks increases. So I would write it as transfer of stress from reinforcement, Okay, now you'd say that as it is transferring the stress, then the concrete will, in the concrete the stress will increase. No, it is becoming more stiffer due to the transfer of stress from the reinforcement between these two cracks. Okay, so it is try to make it more stiffer. So this concrete here become more stiff. Okay, so this phenomena of transmission, or you can say transferring of stresses from the reinforcement between two cracks. Remember, it is between two cracks. This particular thing happens when the concrete is cracked and the reinforcement is provided between, the reinforcement which is provided between these two cracks. This particular phenomena is happening here. So due to the transfer of stresses in the concrete, the stiffening of the reinforcement, the concrete increases. So due to the increase in the stiffness in the concrete, what is happening, the stress which was there in the concrete, we have calculated 𝐶1, we see some reduction in the strain. Sorry, this is strain, so I'm talking about stress. So the stress is getting reduced in the the concrete. Okay, stress is getting reduced in the concrete, right? So we know stress and strain are, as the stress is reducing, so obviously the strain will also reduce, correct? Because they are proportional to each other. So that means the net strain, which is obviously tensile strain. So the net strain due to what should I say? Tension stiffening. Why tension stiffening? Because this is tensile stress which is being transferred, right? So tension stiffening of concrete. So this net stress is actually, and this is actually what should I say? This is a EM. We will write it. So, okay, so it is nothing but, what should I say? Design. It is a means. I would write it a proper way. Let me just write it a proper way. So that it will not create any confusion. Due to tension stiffening, okay, we understood the tension stiffening. What is tension stiffening? So now due to tension stiffening, we see reduction in stresses in this, reduction in tensile stress in the tensile stress in the concrete, here, right? Okay, so if we consider that reduction, so the reduced strain, obviously as the stress is reducing, the strain will be reducing. So the reduced strain, if we consider it as 𝐶2, okay, so the mean tensile stress in this concrete, so mean tensile strain in concrete, where we are calculating the crack width, where crack width is considered, so this we define as 𝐶m. So how much it will be? First of all, we got 𝐶1, which is the actual strain there, tensile strain, and due to the tension stiffening of the concrete, so there is some reduction in the stress. So corresponding to that, there is some reduction in the strain also, right? So that strain will be reduced, we are going to reduce from the strain that we have got first of all at the first calculation, right? Epsilon 1. So it is E1 minus E2. Now the code has given the value of this E2, which is reduction in the strain. So this E2, the code has given, if you see here, it is nothing but this one, this particular area. Okay, so what is this? B minus B into H. We have already written actually here, if you see, we have already written here the formula. You can see B into H minus, I'll just write it here, B into H minus X by A minus X 3 ESAST. Okay, 3 ESAST D minus X. D minus X. So if you just replace this, so finally we got this formula. EM equal to epsilon 1 minus this B into. So now what we can do, okay, let me just write it, H minus X, A minus X 3 ESAST into D minus X. Now we know that H is equal to D, which is my total depth, and what is A, where we are finding the crack width, okay, from the compression phase. So that is also equal to D, so we can say A is equal to D. Okay, so if we just replace this, we will get EM equal to epsilon 1 minus B into D minus X square. You know why? Because if you just replace this here, we can write it is B into D minus X into D minus X, okay, divided by whatever it is. Okay, so you can say B into D minus X square, H is divided by 3 ESAST. ES is nothing but modulus of elasticity of steel, okay, 2 into 10 power 5, right, into D minus X. Correct? So this is the final formula we got, and we know how to find out E1 also, I mean epsilon 1 also. We got this epsilon 1, FST by ES, A minus X. Okay, we have already redefined here, FST by ES D minus X into divided by small d minus X. Correct? So now what is the unknown value? So the unknown values are my FST. What is the unknown here? Unknown is nothing but my FST, right?